Here's our introduction to sequences. In this course, we're going to learn mostly two types of sequences: arithmetic or arithmetic sequences, as well as geometric sequences. Just a few definitions here to get started. An infinite list of numbers with a definite order is called a sequence. Each number in a sequence is called a term. We're also going to talk about explicit formulas. An explicit formula is an equation written in zero-term form. We'll talk about what that means. And we'll talk about a recursive formula, which provides any term of the sequence and how to attain the next term. Again, the types of sequences that we're going to study will be arithmetic sequences, a sequence with terms generated through addition or subtraction is an arithmetic sequence, as well as geometric sequences. A sequence with terms generated through multiplication or division would be the definition of a geometric sequence. First, we'll talk about arithmetic sequences. In an arithmetic sequence, the explicit formula is going to be comprised of a generator. The generator is going to be what is being added or subtracted to each number in the sequence. We're also going to talk about n as the term number, and the IV is an abbreviation for the initial value or term 0. The recursive formula, we're not going to do a lot with this, but I would like you to take notes on it. Gen is still the generator. A sub n would be any term in the sequence, and then a sub n plus 1 is how you get the next term. So first, let's do some examples here of arithmetic sequences. In this first example, we have the sequence of numbers 1, 4, 7, and 10. So what we're looking for here is the pattern of how those numbers are growing or how you're getting to the next number. In this particular case, we're adding 3 each time. Now this is a little bit easier to do because I'm telling you in the title of the section that we're talking about arithmetic sequences. If you did not know that, you would be trying to find what the common difference is between each of these numbers and seeing if there is some sort of relationship there in that common difference. So, if we had to write the next 3 terms of this sequence, we would write 13, 16, and 19. If I were writing the explicit formula of the sequence, the generator would be what I'm doing to get each number, to generate each number, and that is plus 3. And the initial value would be whatever the 0 term of the sequence is. Well, right now I don't know the 0 term. I know the first, the second, the third, the fourth term. I'm just using counting numbers here. If I wanted to get the 0 term, I would have to go backwards 1 spot. In this particular case, if I'm adding 3 going forwards, going backwards, I'd have to minus 3. So negative 2 would be my initial value. Writing the explicit formula is no more difficult than just saying a of n equals 3n plus negative 2 or minus 2. Where do those numbers come from? The 3 is the generator. That's how it's changing each time. The minus 2 is figure 0, or the initial value. The next example you see here, a little bit different. I have some decimals involved. There's nothing wrong with that. In each of these, I am actually adding 2.5, 2.5, 2.5. I can continue to add 2.5 to each of these, and I would get 23, 25.5, and 28. The 2.5 is my generator. To find my initial value, I'd have to go backwards 1 spot from 13. 13 is my first term. 15.5 is my second term. 18 is my third term, the third number. The 0 number would require that I go backwards 1 time, which would be minusing 2.5 away from 13 to get 10.5. Again, writing that equation then is no more difficult than substituting the generator, 2.5. N is my variable. 10.5 is my initial value. Last, for geometric sequences, I have this sequence of numbers, 27, 23, 19, 15. As I can see, this sequence of numbers is actually going down or decreasing. So as I'm looking for that pattern, I'm looking for a minus, in this case 4, minus 4, minus 4. So the minus 4 is my generator, negative 4. If I need my initial value, which I do, to write the explicit formula, I would have to go backwards one time from 27 because 27 is my first term, 23 is my second, 19 is my third, so forth. So to go backwards from minusing 4 would require that I add 4. So my initial value in this sequence is 31. Now a lot of you could be looking at this and saying, oh, well, this is a lot like mx plus b, which is something that you probably learned about last year. And you're right, it is almost exactly like mx plus b. M being the growth, negative 4 being the generator, 31 being the initial value or the starting value. Arithmetic sequences. Geometric sequence. The explicit formula is a little bit different. Now we're talking still initial value, okay, which is still going to be term 0. But now we're using a different word here. We could still use generator if we wanted to, but I like to call it multiplier because in a geometric sequence we're multiplying to generate the next term. So multiplier, I think, sometimes makes more sense. And in this particular case, you see that n, the variable, okay, is now an exponent. The recursive formula you see is very similar. G sub n would be any number in the sequence. G sub n sub n plus 1 is how to get the next term, and the multiplier is the multiplier. So I'm telling you they're geometric, so that makes it a little bit easier here, but if I strike out with finding a number that adds to make the next number, I should always try multiplication next. In this particular case, 3 times 3 is 9. 9 times 3 is 27. Times 3 is 81. So my multiplier is 3. Again, 3 is my first number. 9 is my second term. 27 is my third term. 81 is my fourth term. I would have to go backwards to get my 0 term, which requires that I divide by 3. Now this particular case is unique because dividing 3 by 3 would actually give me 1, and nope, that still works. So my initial value then is 1. So if I write my formula then for my explicit formula, I would have g of n, I'm just calling it g because it's geometric. That's going to equal my initial value of 1, my multiplier of 3, and now my variable n is the exponent. So I need to make sure I write it high enough that I know it's an exponent. Sometimes it's a little more difficult than just looking at it and seeing, oh, times by 3, times by 2. Those are the easy ones. This second one here is a little bit tougher because when I'm sitting here thinking about this, I don't know that there's a number that comes to my mind immediately. So when I multiply 4, I get 6. When I multiply 6, I get 9. Multiply 9, I get 13.5. So if I'm struggling with that, I can always divide any two of these numbers to determine what my multiplier is. What I mean by that is if I took 9 divided by 6, I should get my multiplier. I'm going division backwards, right? Multiply forward, division backwards. So when I take 9 divided by 6, I should get 1.5. I would want to test that with a different selection. So 6 divided by 4 should give me the same multiplier. And if I do that, I get 1.5 again. So now I know my multiplier is 1.5. If I want to get my 0 value, I'm going to take 4 and divide it by 1.5. When I do that, I will get my 0 term. And in this case, I get a sort of a messy fraction, but I can always change it to, or a messy decimal. I would probably be better to change it to a fraction. And we've talked about that in here enough to know. So 8/3 is my fraction. Now, if you would write the decimal for it, I certainly would not take points off. Or if you'd write it as a mixed fraction, that would be okay as well. I'm going to call it g of n because it's geometric. My initial value, I'm going to say, is 8/3 because I know that's Mr. Warner's favorite answer. My multiplier is 1.5. And my variable is the exponent. That's a geometric explicit formula. Last one here, you notice that my numbers are now going down, which probably means I'm looking for division instead of multiplication. However, what I will tell you is that the most accepted way is to always write this as multiplication. So remember that dividing and multiplying by a fraction are actually the same thing. So what fraction can I multiply 48 by to get 24, 24 by to get 12, 12 by to get 6? I should be able to quickly look at those numbers and recognize that. If I can't, again, doing the old 12 divided by 24 is an option. And that would tell me my multiplier is 1/2. My initial value, again, 48 is my first number, 24 is my second, 12 is my third, 6 is my fourth number. If I went backwards to get my 0 number, I could just follow the pattern backwards. 6 times 2 is 12, times 2 times 2 times 2 would give me my 0 number of 96. I'm calling it g of n because it's geometric, and I'm saying that it equals 96 times 1/2 to the nth power. And last here, before we move on, are just a few examples. I'm asking you to write the next 3 terms of the sequence and find the initial value. I'm not asking you for formulas for this one. We'll do that on another day. But real quick, just to recap, I'm looking to see if there's a pattern from one number to the next. All right, that's the first thing that I look for. Is there anything I can add to 5 to get 14? The same thing added to 14 gives me 23, and so forth. In this case, my generator would be adding 9. So if I was writing the next 3 terms of that sequence, I would write 41, 50, and 59. My 0 term would go backwards 1 to get -4. Next, I noticed that 6 to 18 is adding 12, but 18 to 54 is a bigger jump than that. So I would want to probably look for multiplication. 6 times 3 is 18. 18 times 3 is 54. And then to write the next 3 terms, I would just continue to multiply by 3. I would get 162, 486, and 1458. To go backwards one time, I would have to divide by 3. That's how I get my 0 term. And 6 divided by 3 is 2. This next example here is a little bit trickier. We had this one in the packet in class. 1 to 4 adds 3, 4 to 9 adds 5, 9 to 16 adds 7. So you notice that the numbers I'm adding is actually changing this time. And there's a pattern there. So the next one should add 9, which would give me 25. Add 11 is 36. Okay, and then add 13 is 49. If I went backwards 1, I would subtract 1 from 1 and get 0. Now there's actually another pattern for that. If you didn't pick up on it in class, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, so forth. So if I keep squaring numbers, that's where I get this. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, and so forth. And the last one is one that I think some people struggle with in class. 1, 1, 2, 3, 5, 8. Sometimes sequences don't fit into either of these 2 generalizations, arithmetic and geometric, so there's some other sort of pattern here. In this particular case, is a special sequence called the Fibonacci sequence. And to generate this sequence, I add the 2 previous numbers. So 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13, 21, 13 plus 21, 34, and continue. 21 plus 34, 55, so forth.